All right, in section 6A, at least I hope it's 6A. It's been a little while since these have been filled in, and I'm getting a bit confused on which ones I'm looking at. Anyway, regardless of whatever it is, what we're going to be looking at is distribution of data, and these are the types of pictures that you're going to see at the beginning, these little curve looking graphs here. These are also looking like histograms a little bit later on. As we go through things, you can kind of imagine the curvature is just kind of outlining the top of a histogram. So as we go through everything, be thinking that we have a histogram. We have bins and we have frequencies and all of that stuff here. All right, these two pictures, oh, let me go back up to the top. The big three things that we're going to look at are going to be the shape, the typical value, that's like the best representative of the data that we get, and the variation is like a spread, how wide does the graph go. Okay, these two pictures are very common for what we'll run into with these distribution type graphs. Before even answering any of those questions, now you should have already done the activity and hopefully you've investigated these things. But the big difference between these two is that this one is symmetric. It's got this single mound that's up in the top here, and we describe it as like a bell-shaped curve that just from that peak, it symmetrically, or as very close to symmetric as possible, it looks like it just kind of expands out and then lower. So you have a high frequency in the middle and then it drops as it moves around from there. The second graph, you still have like a high point, so a lot of data is going to be around there, but the way that it decreases around it is different. It seems to drop a little bit more in that front side here, and then over here it takes a while to drop back down to 0. All right, answers to the questions here. How would you compare the left and the right sides? They're the same for that one because it's symmetric. The number of mounds that you have, you can have 1, already described that. Number 3, how is this one similar to the previous? It does have a high point in an area, but what's different about it is that it trails off to the right over here. All right, what that is referred to, and you'll see it in just the next part here, is it's called being skewed. This one is getting skewed to the right because it actually is going to the right in the direction that it trails off. So it trails off to the right, like that. Again, you've probably already done the activity or you were assigned to do the activity originally anyway. You're also going to discover a little bit later on in the activity, or you would have, that to be skewed right means that you might have an outlier out here, a single value that's just hanging out over there, and the whole graph curvature has to adjust just to fit in that single value or two that might be out there. This part's going to talk about your skewed right and skewed left. This graph is going to be skewed right because it is getting pulled in that direction to that way. So you could imagine another graph that starts low and then has a high mound over there, and this one would be skewed to the left because that tail end goes to the left direction. By the way, every time you read these graphs, be thinking that these are low numbers and these are high numbers on the x. Sometimes, depending on the context, you want almost like high numbers, like if you're looking at grades, you kind of want high numbers in the front and then show how it trickles off to the lower ones. But this is always going to be the high number and that one's always going to be the low. So usually, like, we hope grades, when we grade you, would be something that is skewed left. And you kind of think about that, what that means. Okay, some graphs here just describing, and all of this stuff that we're talking about right now is the shape. I didn't read that little title part at the top, but this is all about the shape, whether they're symmetric or if they're skewed. The graph in the middle, this is going to be symmetric. It is not perfectly symmetric. If we made that little bell shape that goes around it, it may appear to skew just a little bit to the right, but when we're talking skewed right, we're talking like there's obviously like these extra values like hanging out to the side. So if you were to draw that curvature around it, all of a sudden it goes, it pulls way out to that way. Okay, so that would be skewed right. This is going to be considered symmetric. You basically, above the high point, you have almost the same amount of spacing as you would around it. Okay, so it doesn't need to be perfect. Be very clear on that. This is going to be skewed left. This one's a bit of a tricky one because you get that high point almost in the middle of like everything that's there. But you've got a few other like high frequency bars over here. Right, so if you were to trace the outline of it, seems to have this crazy drop there. But it's about these outliers. This guy over here and even this guy that causes it to sort of trail in that direction. That one's a bit of a tough one, but it's definitely not symmetric, right? So we're going to look for, usually the way that it gets skewed is where you're going to see your lower frequencies, okay? All right, continuing to look at the shape of the graphs, we're going to discuss a little bit more about how you might imagine whether something should have a skewed graph or if it should be a symmetric graph. So these three questions here that they're going to describe, we're going to make that decision. Basically, what you want to do in these is to think about all the different possible values that you could get, and like, could you really possibly get from the thing that's being asked, and then ask yourself if, like, on one end or the other, on the high end or the low end, do we expect a lot of data, and then on the other one we expect very, very few numbers for that. Okay, so A, on an exam where most people scored very low, so they went ahead and told you how the exam score went, you have a lot that score low and only a few did well, okay? The fact that you don't have an equal amount of how people did well or did not, you can have that mound shape on the low end, and then it's going to trail off to the high end here, so that's going to be skewed right. This is not something we would want to see if we were given an exam, because that means that something did not work, because we have a lot of low scores and then only a few people who did really well. We'd usually, for an exam, want to see like the opposite, or really like a symmetric graph that'd be on this side, but that's how that one's described, having a few do well, so it trails off on that high side there. All right, next, the ages of all CEOs of Fortune 500 company. For this one, I needed to even ask my wife like what she thought about it. I said, hey, what would you think about the ages of the CEOs of Fortune 500 companies? And she said, oh, they're all old people. I was like, okay, that's what I kind of thought too. But it's possible, right? It's possible that you could have a few people that are really young, you know, with social media, different companies and stuff like that. You're starting to see like people that are really like young coming into these big companies. So this one is going to be skewed left. We expect most of the CEOs to be in their to have higher ages. I don't know what age that might be, 60s or so, 50s, 60s, but we'd expect that. But you may have people that are like just coming out of college. They could be mid-20s, early 30s that are also CEOs. So there's a few of them that would be down here, but not typical of what you'd expect. So that one's going to be skewed left. Remember, you're always going to have low numbers to high numbers. Okay. All right, last one, the weights of each banana in a shipment. Usually bananas are generally the same size. There's going to be some you might say a little bit larger, some that are smaller, but you're not all of a sudden going to find this banana that's like twice the size of others, or one that's the half size ones, assuming that we take out those little miniature ones that you see at the produce store. All right, so that one is leaning towards being symmetric, that there's going to be a nice balance between like the weight. You can have most of them at a certain weight, and then what you have that are heavier is going to be about the same amount that you can have that are going to be lighter, so a balancing in that part. All right, next what we're going to talk about is another way that you can identify if you're going to have some sort of skewness on here, and that comes from whether or not you have a natural minimum or maximum. By the way, in this part here, there's no like rule that says to have skewedness, you have to have these things. This is just saying that if what we're looking at does have a natural minimum or natural maximum, that means numbers that you can't go below or numbers you can't go over, that you can get skewedness. And there's cases that, like say if you're talking about grades from 0 to 100, you have a natural minimum and you have a natural maximum. That doesn't mean you're going to be skewed in both directions. That would end up meaning that it was symmetric anyway. So don't let this be a rule that tells you that has to occur to get skewedness, okay? All right, so we're going to make some decisions here. The set of all incomes for recent college graduates. Usually when we talk about that, we say you're going to get a starting salary when you begin your new job, and it's not going to be like that great of a pay, but you know, of course, it goes up from there. Okay, but we're looking at the time when you first come out of college. We don't expect students to get paid a lot. However, there are going to be some that get paid much more. So this one sort of has like a natural minimum that we expect that when you do come out of college, you're getting paid a certain amount of money. You shouldn't be getting like maybe I want to be careful on to say it, but it shouldn't be like a minimum wage job that you're getting from this. So there's a general number that we're expecting that you should be making, maybe 35 to 40,000. But there's going to be some people that are going to make a lot more. So this one's going to be skewed. It's going to be skewed to the right. You have a minimum that we're sort of expecting that people should be making when they come out of college, but you can make a lot more. A lot more. Oh, the next question asks like whether it's going to be skewed or which direction. So it's a natural minimum, and then it's going to be skewed right. Didn't quite read the blanks when I was filling those in. Okay, B, the ages of children in a 12 and under elite basketball league. The way that they write it, they're really leaning towards that natural maximum. Once you get to 12, you've got to be out of the group, okay? Now, then you've got the debate of like, you know, how young do we think kids are going to be that are in this? Because I bet there would be just as many like 10, 11, and 12-year-olds that are in the league, maybe even 9-year-olds. But you might have like some smaller groups of students that are, not students, athletes that are younger. So this one will be skewed left because you have that maximum. Because that maximum is hit at 12, you definitely have the opportunity of, you know, a few that are in the younger group there. So that one's skewed left. These are a bit tough, just to be clear on. I think some things are much well defined as maximums and minimums and like a reality sense of what you should get. All right, 11. This is interesting stuff here. In all the graphs that we've looked at, we've had a single mound. Like there's an area where a lot of the frequency is clustered. Remember that these are like histograms. Okay, so you get like high bars wherever there's these mounds, and then you get low bars in other spots. So the graphs that we've looked at, most of the time there's like a peak where a lot of things settle around. But it is possible that when you look at all this data, you can have two different like peaks in there. You could have a lot of like low values that center around something, and then you can have a lot of high values that center around another number. Without a contextual problem, it's a little bit hard to describe like how you get these separated here, but I know it shows up in a little while. This case here, they're not equal size mounds, so you're still really heavy in this sort of low number area, but for some reason, there's a peak at like another location over in that area. Again, without an example, it's a little bit hard to explain, but it's possible. It doesn't have to taper off. You don't have to force, if you see a dip in the bars of the histogram, you don't have to force it just to kind of go over that and trail off. There's sometimes a lot of value in understanding why there's another high point in places. All right, these a little bit odd. To describe multimodal, by definition, multi means many, so you could have like a bunch of mounds in there. There's a chance that you don't have two, you could have three, you could have four, you could have all kinds of stuff. At some point, if the graph becomes uniform, that means that it's really just similar heights across. Like if you just had a bunch of little mounds going along, that might not tell you really much about what you're looking at, or it may tell you a lot, as in that that there isn't like a spot where most of the values gravitate to. So many modes or mounds, modes, you could all say that. And then this is getting close to almost like a straight line as you graph. All right, in 13 and 14, what we're going to be looking at is the width of the bars of the histograms. So at this point, you didn't really get any pictures of the histograms. We were just looking at the curve shape to it, and now we're looking at like a little bit more into the detail of what would be happening in the histogram in those spots. The question that you're asked about this first graph is whether it is unimodal, bimodal, or multimodal. that may have been defined on the previous page and I missed it, but unimodal means that it has a single mound. This means that you have two, and then that just means that you have more than two mounds that would be in there. Okay, so as you look at the graph, you can maybe imagine drawing that curvature where it hits a high point and just skews off to the right. Like that would be sort of a reasonable thing to see here. However, and now this really comes down to like a judgment call, that dip that's here in the middle, we need to really ask ourselves, is that important, right? Is there a reason why we have a high point here, we've got a low point, and then a high point there? And a lot of this just kind of has to do with what the topic is and whether you should pay attention to it. What we do want to say in this graph, though, is that that's a reasonable thing to see if I can even draw the curve over it. It's reasonable to assume that you've got the second bound there. So we want to call it bimodal. Now, if you look way over here to the side, there's another little like bump that's in the graph. I don't think that would be enough to say that it was trimodal or multimodal, whatever word you want to use for that one. This is a big jump up until that spot, and then there's a tapering off of it. This is just like we went up by a couple numbers and then back down, okay? Those shouldn't be things that we make like a big stink about with whether it's another mode. That's tiny compared to what's going on in these other areas. Okay, 14 is actually the same graph, or the same, not the same graph, obviously, it's the same data that they use. But what they did is they took the bin sizes from being really thin to making them about twice the size. For these numbers, I said that in the first, the bin size is about 20 minutes. You just kind of have to guess what you want there. And then for the next one, they said that it was 45. But so it's the same data. It's the same data, but what we're doing is changing the bin sizes of that. When you make the bin sizes wider, you're going to be grabbing more data to put into the same bin. So what you're going to see is, one, look at the high point here is at 100-ish. The high point here is at around 150. That's because what was in this bin is now gaining some of the stuff that would have been around it. I'm not looking at the exact details, I'm just describing generally what could happen. I don't know how they have them blocked off at their spots here. That one starts after 100, that one starts at 100. So, but there's this blending of some bins together when they do that. And the neat thing that happens when you do that is sometimes you lose that bimodal shape. Now this one really just tends to be unimodal, and then it's going to be skewed off to the right. Okay, let's see what questions I haven't answered here. Why does the maximum value of the frequency change from the first to the second? That's because we got more things going to the same bin. C, how would you describe the second graph? Unimodal, bimodal, so that one's unimodal. D, explain how making certain decisions about when constructing graphs can impact how many mounds you input. So this is coming back to whether we use wide bins or we use narrow bins. The wider the bins that you have, when you use wider bins, you're going to hide some of the detail, right? When you look over here, you get to see that drop and then that kind of build up, and you even get to see that little bump at the end. Again, not too important, but you get to see all these little things that are changing in there, and you lose that in that one. So there's a drawback to the wider bins that you're going to lose detail, but at the same time, you don't want to make them like so skinny. We talked about that when we first introduced histograms. I forget which section it was, but like if you had a bunch of test scores that are all different, there's no point in making a histogram because all the bars are going to be the same. So there's a fine line between like what is appropriate and what is not, and it really does come down to what is the context of the thing that you're looking at. Okay, 15. We actually get to do context problem now. In a military base, you have on-base housing, you also have off-base housing, and then you have, and this is a real key part here, you have a small number of families that also are living in non-military housing. So these people would live further away, and I actually know this from being a kid and living on Bergstrom. You know Bergstrom as an airport now, but it used to be an Air Force base, and we lived on base housing when we were there. And then eventually my parents bought a house that was that was further out. Okay, so they ask about commute times and what should we expect. The on base, you're going to have a very low commute time, so that mound is going to be close to the beginning here. Okay, you're going to have, it may even be pulled even closer to that one. I just wanted to make it look this way. But the on-base housing, you're going to be super close to your job, to the point you can probably walk or bike to whatever building you need to get to. If you are off-base housing, you are going to have to drive and commute, and you're going to have to go through that security gate to get in. So these people, their drive is going to be a little bit longer. But we're expecting that there's almost like an even split between these two. Okay, so it wouldn't make sense to have them just combine together and make a single mound for those types of people. These are, it tells a better story to understand that there's some on, there's some off that take longer to drive there. But then you're even going to get this skew to the right behavior because of those few families that live non-base housing. Now, if that number was supposed to be the same as those who live on base and the same as those who live on off base, you could get a third mound, but it said that they're very few, so these are just going to trail off in that direction. Then I answered that question there. Is it symmetric? No, it's going to be skewed to right. By the way, though, you can, if we took these people out, if we took them out, if they were not part of this at all, and you just remove that, then you could still get what's called a symmetric bimodal. You know, even size bumps here and there. Again, it doesn't have to look completely symmetric, but if those mounds turned out to be the same height, then and you took these out, then you could actually have symmetric with bimodal. Okay, 16. We finally get to talk in the notes about what are outliers. I've mentioned them a few times before, but now we get to see them here, and they give you very exaggerated pictures of it, which is very good for us. The first, the outlier is that one that's way out there. I mean, you've got a high number over in this area in the frequencies of 40s. Then you've got immediately after that frequencies in 30s. There's a significant drop into the next bin. Not anything that's too unusual. But then it skips forever, and then there's this one that's hanging out there. So all we know that it's a weight. Something that's really heavy, that's way out there. So that's an outlier. Also have an outlier that's here. Okay, and the next part, what we're going to start talking about is a typical value. And the thing about outliers is there's a couple calculations that we're going to look at in the next part of 6A, mean, median, mode, and all that stuff. And outliers are really bad business when you're talking about a mean, when you're doing an average. But if you're talking about a median, which is called the middle number, I hope you remember a little of this stuff here, the outliers aren't such a big deal. When we start looking at the typical value of center, yes, we have a value that's way out there, but we sort of take that value and the very far end other one, and you use them to kind of like cancel each other out. And then you take maybe these two dots or those two dots and you cancel them out, and you start to move your way in until you find like the true middle of where all the dots are. And that's usually pretty close to where your high mound is. But you're also going to see later on that when we do means, when we include these really high numbers in and then divide them, it can actually throw the typical number off into a bad direction. So that's a little heads up on things that are coming later. Okay, so your typical values. As we start to read off numbers, I know it gets there towards the end of this part, you're going to have numbers at different boundaries here. So if you wanted to talk about a certain bin, let's say we're going to talk about this one right here, this bin, don't give it a range of 15 to 18, because remember you have that right-hand rule that means that 18 falls into this category. This example is going to refer to the number of soccer goals, so you've only got whole numbers that we're looking at. That means that this bin, the one that I'm pointing to, with the right-hand rule is 15, 16, and 17 goals. 18 goals is actually in the next one. So you want to be careful that if you're going to choose a bin or describe like a range of values, that those boundaries, you actually have to subtract one from them. And hopefully I got all those right when I did my solutions as well. Okay. They say that the typical number is around 16, which is about here. Okay, the main thing that we want you to take away from this at the moment is if I cut it in half this way, look at the width of that. Okay, I've got a little bit of a width, but then if I look at this side, the width, the spread of this whole thing is much bigger. It's almost like maybe 2.5 times as wide. But what seems to be the same is if you were to add up all the sizes of the blocks, they seem to be the same amount of area that we've got. Okay, and that goes along with what we call the median, where you locate the middle of things. So even though that number is really far out there, it gets balanced with one of the numbers at the beginning. So the way that we usually find the middle of a skewed type histogram graph is to divide up all the area. Sometimes it's easier when you've got all these little dots and you can just, count off dots from left and right. Do you imagine it here? All right, B, what if you describe the center as 15? Is it reasonable? Sure, I think that would be fine if you just moved it over. It's not too much of a big deal. But if you're going to pull it in that direction, usually what I think that you're doing is trying to eliminate the outlier. I don't think really switching from 16 to 15 is that big of a deal, and I think anybody can really make that judgment call. They're technically in the same bin anyway, right? But when I read the question, maybe I was just imagining, okay, if we took that guy out, I think moving it right to the 15 line sounds a bit better. Question C, would it be reasonable to say that it's 18 or 12? The answers to those are no. 18 appears to be a little bit more of like the middle in like the horizontal axis, but you've got high points over here and you've got a lot of missing stuff there. So you don't want to move out to the 18, and then 12, 12 technically falls into the larger one, but I don't know, it's too far over to the left for you to say it's me. You want to split the area, that's the thing. All right, D, the typical number of goals is somewhere between blank and blank. So even though this is like the highest point there, you've got two good sized bars just to the right, and you've got one like even shorter than those two there. So I don't think that we should say that the range is just in the highest point. If it was a symmetric graph, yes. If it's skewed, you want to move a little bit over to that skewed side, and it'll probably fall inside that bin that I kept pointing to here. So 15 to 17, remember not 15 to 18, because 18 is actually in the next one. But if you happen to write 15, if you happen to write 15 to 18, that's fine. It's all subjective. That's it. But it's usually going to be just to the side of whatever your highest point is, and it's going to be to the side where it's getting skewed. That's an important thing that we'll see. 18 is one last look at a typical value before we move on to variation and the spread of the distribution. All right, this histogram, what I do see here is a high point right there, very clear high point. It drops a little bit to this side and then trickles down that way, and it seems that there's no values, but then there's a couple here. So even when you look at the frequencies, these aren't high numbers. It's only a 7, that's a 2, that's a 2, and then that's a 1. So it does not ask about the shape, but I would argue that the shape here is symmetric. The interval, though, for the typical value should be 12 to 14. There's this obvious one high point, and then it seems to balance around it. Even with that missing spot there, having 2 over there and then 2 and a 1, I think it's a fair balance in these things. All right, next we're going to talk about variation. Variation is the spread of the data, okay? This picture shows the heights of family members that look like these people. This shows the heights of a family that looks like these people here. If you did histogram, their heights are all basically the same thing, so they just get stacked. 1, 2, 3, 4, frequency of 4. Over here, and they basically use the same spacing that they did on the x-axis, which I guess is good to know. But their heights are all like in different spots. So you got 1, 2, 3, 4. So you still got the total number 4 people, but they're all at 1. Okay, so this one does not have much variation. This one has a lot of variation. What do you think variation means? It's a difference in values. And usually on the graph, you just see it as how far to the left and the right this whole thing is kind of spread out. Okay. All right, let's see here. Family one, these people here have very little variation, right? They're all in the same bin. Their heights will range, and these are kind of hard to estimate, but I just said around 68 to 71. This is what I call them. I didn't even really worry too much about making sure that I fall back a number because you can't quite tell where the boundaries are. Okay, but family two has a lot of variation, and they're going to range all the way from about 44 to 71. So just, you know, the point is these numbers are very close and that these numbers are very far apart. Question 20. Where's the little question here? Which resort had more variation in the number of days guests stayed at the resort? Variation over here. Okay, so there's a little bit of a contradiction to how I described it in the last one. In the last, I just said, hey, spread. And that's a nice way to look at it, is how far things are pulled apart. Here, 2 to 16, 2 to 16. It's not just about minimum to maximum. That was called range back in like junior high level math. The range is still from like 2 to 16, 2 to 16, minus the right-hand rule business. But you've got this very high point in the middle here. These two boxes around them are, they're all right heights. But then you've got it like this drop off, and then it's just almost like an outlier hanging out here. Where in this guy, it's almost consistent across how much you have. So you've got these three here that are all reasonable height. It doesn't drop much here, drops a little bit there. And then even like at the far end, you don't have like a really low value like you saw in this one. So the spread isn't just really the range, the low to high, but also like what the shape is within that area. This doesn't have much variation. It's very heavy here. And there's a few things scattered out to the side. This one's just pretty much all over the place. Without it being just a straight line across, it's okay. There's not too much change in there. So anyway, more variation, less variation because of that high point. That's it. All right, here we are putting it together. You've got shape, you've got a typical number, and you've also got variation. Those are the big three that we're looking at. So I got all these filled in. You can read them in just a minute if you want. Oh, this is cool. It goes back to the soccer goal stuff, and we have the women versus the men for the soccer goals. Okay, in the women's, this with that outlier out there, and even from the high point, a couple tall stacks, and then going that way, this is going to be skewed right. You've got that mound that's here. Okay, and then it's going to slowly drift off, and then you've got that outlier that we have to include over there. So that one's going to be unimodal. It's got one mound on it, and it's also skewed to the right. The men's graph, you want to almost draw a graph that's like skewed that way, right? It goes like this because you see it sort of trail off. But when we try and include the other ones over here, there's actually a fairly decent balance in this one. So though it's not perfectly symmetric, you would say that this is symmetric, and it also is unimodal. Let's see. What other ones did an answer? The women typically scored about 12 to 17 goals, so that's where you're going to take like the big cluster that you have. So 12 to just before there. So we're taking in that area. That's where that high peak is going to be located. The men are around like that one tall bar that we've got there. So the 12 to 14-ish range. And let's see here, not including the outlier, which is way over there. That's the only graph that had the outlier, 33 to 35 bin. The variation, the number of goals scored by women was the same as the variation of the men over there. So And that's just, if you take that one out and you kind of cut off the graph, your range of values really isn't too different than what we're seeing there. They're different, but not so much. Yeah, so again, for the women, then you could describe it as having more variation generally, and then the men doesn't have quite as much. But that's due really just because of that outlier. All right, last question for this part, 22. I should probably have covered some of the answers, but I'll just let them be there. All right, 22. Consider the data set containing the number of piercings for each student in a large sample of college students. Okay, now, without actually having the data, there's a lot of assumptions that you're making with what you believe the answers could be. So I totally understand some different arguments and stuff, and maybe I don't know. Maybe I'll just keep to my answers, and then I'll see if I think to say other stuff. But if you have different answers that you think are justifiable, when we come to class and we talk about things, this could be one of those parts you say, well, I drew it a little bit different. I consider this, and I think your argument could be fine because I know that there's other ones out there. Okay, the way that I imagine is most people with piercings. Let's see, does it say that they're even girls or boys? Piercings for each student in a large... Okay, so it doesn't even tell you if they're boys and girls, but boys, there's going to be a lot of boys that don't have any piercings. 0 is your answer. Okay, a lot. And then you're going to have... And of course, if you grew up in the late 80s, early 90s, as I did, many boys will only have 1 piercing, right? You might not know that one. But girls would typically have 2. Now it's more kind of cool to maybe have 4, like 2 in each ear, something like that. But we don't expect that many piercings in people. Then there's this other group, the other group of people who really have lots of piercings, okay? So the way that I would expect as far as the peaks for this, I'd expect to be 1 peak. Of course, this all depends on the width of the bars, but I'd expect 1 peak that's more around like the 2 piercings. So it's going to trail off in the front around 0 and 1. Not too much, but there's going to be a really high point at 2, and then it's going to get skewed off to the right for the people that have like this exceptional number of piercings. And again, some of that, okay, so 1 peak, skewed right is what I think here, and this is the graph that I imagine. Some of that really depends on who the people are that they actually got in the survey. I know it's a lot of college students that were asked, but there's also a chance that when you ask a lot of students, you could run into, many people that have 5 or 6 piercings, sort of thing. And then there's another time you could do the survey and run into just a few people that have multiple piercings. So this is the way that I imagined it. Most is going to get... I said that was around 2, with the consideration that it might also be involving guys. Then I'd maybe place the 2 like in that area. I don't know, so that you've got... It doesn't mean that there's a high point at 1 either. Well, 0 would be there, so that doesn't make a lot of sense. Look, I'm going to mess up my graph here at the very end of this part of the activity. But what I was trying to get at is that you're not going to have many at the beginning. This will probably be super steep right there. But it'll trail off for the few people that have lots of piercings. All debatable. If you have different thoughts on that one, then feel free to share your thoughts. All right, 6A2, aka pages 7, 8, 9, and 10. I think they just split these things up to make it seem less intimidating, but you're not tricking us. There's 10 pages here. Okay, we're going to talk about mean, median, and mode. I remember these from a long time ago where you'd get asked these questions, mean, median, mode, or range, and hopefully you never answered range because that was never the answer to the problems. Okay, mean, we remember that one as average. Okay, the median, we remember that one as the middle, and the mode is going to be the most common that you get from data. Okay, so you're collecting data that's quantitative, those are numbers, and averaging things is where you add up all the values and then you divide by the number of values that you got. That part does get explained here fairly well. There's some nice little details in it. But you do add everything up and you divide by the number of items you have, and that becomes your representative number for whatever you're looking at. I don't think it refers to it in this activity, but I remember that being called the measure of central tendency. Okay, the measure of central tendency. Oh, that's a neat little symbol there. That's called X bar. It's just a way of describing mean. Different notation that you might not have ever seen. It's called X bar because there's a little bar on top of it. All right, median. Let me go ahead and pull that one up here real quick. The median is the middle number. What you do is you list all the numbers from smallest to greatest, and then you just move like in until you find the middle number. Okay, couple odd cases though. Well, the first one's not odd. If you have an odd number of items in there, it's just going to be the middle number. Okay, you're going to get rid of the lowest and the highest, then the next lowest, next highest, until there's only one in the middle. But if you have an even number of numbers, you get stuck with only having two that are sitting in there. So what you do is you split their difference. It's described here as taking their mean, like averaging them, but you can just split their difference. Find whatever's halfway between them, and that'll be it. So sometimes your median is a number in the set, and sometimes your median is not. Sometimes not. If your two middle numbers are the same thing, then there's no difference, and that means that that is your median. All right, and then mode, I'll get to that one a little bit later. That is just going to be your most common item that you see, which surprisingly is actually very cool in histograms. We never found a lot of value in that one in the past, but it looks neat in this one. Okay, we're going to practice the mean or the average a couple of times here. These are the ages of the first 6 chief judges at their confirmation. So you get 6 numbers there. When you add them all together, you're going to get 311. You divide that by 6, and you're going to get 51.83, which you could say is approximately 52. Okay. Here's a histogram that goes with it. I didn't even think about demonstrating this part to you, but 51.3 it's around here in the graph. Okay. It's kind of interesting how it is. I mean, you got that high bar and you got that low bar next to the highest one. So it's going to be a little bit more like maybe into that direction. It's not a set rule or anything, but it's always good to check and see what we've got. All right, number 2, these are going to be the ages of the most recent 6 chief judges. The graph, you can already tell, the scale is the same thing. The scale is the same thing, so it's actually getting pulled more to the right. It does seem to be symmetric, where the other one may be a little bit more skewed right. It's a bit of a stretch. It's not as symmetric as that one. You add these up, you get 372, divide by 6, and you're going to get 62. So the first 6 chief judges were typically 52. I rounded that off. While the 6 most recent chief judges were actually at 62. So the 6 most recent chief judges were typically, I didn't know if they wanted me to put these words in the blank or not, but I thought it sounded cool to say 10 years older, are typically 10, I put years, fill that in there, 10 years older than the first 6 chief judges. Really all this is about, though, is just calculating the mean, just understanding that you're going to add them together and you're going to divide by the total number of items that you have. Okay, the median, as I described a little bit earlier, is going to be the middle number. All right, so these are office managers. Suppose an office manager forms a committee to explore the best way to update human resource. Okay, so these are committee member ages here. All right, and sometimes we're nice to you and we put all the numbers in the right order, and then sometimes we mix them up. It really just depends on how many numbers we give you. If we give you about that many, they're going to be mixed up. If we give you like 20 values, we'll probably put them in order for you just to save you some time on that. And making mistakes just organizing numbers is an unnecessary thing for trying to test you on a concept. Okay, so these are out of order. You needed to rewrite them in the correct order. 41 is going to be the middle. All right, so you take out the youngest and the oldest. You balance with those two, take them out, take them out, take them out, get you to 41. So that's going to be your median age for the committee is 41. All right, B, write a sentence interpreting the median as the center. That one actually took me a little while to think about what I wanted to write because we know the median to be the middle. We know it's like the best, we're trying to find what we call a measure of central tendency or a best representative number, and we're going 41. But the weird thing is the word that always comes to mind every time you want to write a sentence is you want to say the average age. You want to say the average age is 41. But it's not, because that was the mean. The mean was the average, right? And we'll probably get something different if we average these out. So it took me a little while to come up with what I wanted to say, but I went with half of the committee members are younger than 41 and half are older than 41. That was an our way to do it. It doesn't tell you like what those other ages around it really were, but you know that that's the middle age. And I also was trying to avoid using the word middle because I thought that would be a bit too cliche. Okay, so our manager, being so concerned with how people feel, he realizes that there's a lot of employees that are recently college graduates, youngsters, right? And you got these old people. You get these old people on the committee. So he says, let's add one more person to the group. Let's go ahead and add on a kid who's 23. So they went even younger than the one that they got. Straight out of college kid, they put him on there. Looks very good and is probably actually a really good thing for their committee to do that. But they had that person in there at 23. The interesting thing is that depending on how you try and give the typical age of the group, it might not change that much. Okay, remember that in our list before the 23 was on there, the middle number was 41. Okay, as soon as you add on the 23 and we start moving in from the sides, taking out values, we now have 2 in the middle. One of those numbers is still the 41, but the other number is 39. So we're going to split the difference and we're going to say 40. So now what we say is half of the members of the committee are younger than 40 and half the members are older than 40. Not much of a difference from 41, is it? Not really. Okay. Then I put this in a box here because this is one of the really important things that's going to show up in a little while here is that the difference between a mean and a median. Medians do not get affected by outliers, right? I wouldn't really say that the 23 is so much of an outlier. He, she, whoever it is 6 years younger than that one. But you've also got like this person that's, 11 years older than that one. So they're just as much as an outlier. But when you try and add a value that's at the far end of the data, and imagine this way. What if we decided just to, it'd be a stupid idea, but we just put a kid who's 10 years old on the committee. Right? He has no business being on the committee because he's 10 years old. But he's somebody who's 10. It wouldn't change the answer. You still have a 40. Okay, so all this is trying to get us to this other idea that's really important, that if you have outliers in values, then medians might be a better approach than using means. We'll see that comparison in a little while. All right, next we're going to talk about the mode. The mode is going to be the most common value that you see in the data. Now, sometimes you can get a tie. You might have a number show up 3 times and another number show up 3 times. So they're equal, but there's a lot of other numbers that only showed up once. So you could have you could have more than one mode. I don't know where it introduces the words. They'll pop up somewhere around here. But so you can have one mode, you can have more than one mode. If it's 2 modes, or maybe we already talked about it, it is bimodal if you have 2 modes. You can have no mode if there isn't any value that's greater or more consistent than the others, then you can have no mode. And space refer. Okay, and then what this is referring to here is that if we're doing like say you're doing grades on a test and the grades can be any of the numbers from 0 to like 100, you might not get any grades that are duplicates of each other, but you might get a cluster in the 70 range or high 70 range, and then you can make that range of values be a mode. Okay, so that's a way that you would deal with having like just a whole bunch of different numbers. So here's the answers. In the first set, the mode is going to be 12 because there's 2 of those and then only 1 of the rest. In B, you're going to have what is a bimodal because you've got 2 of them. There's a 15 that's twice, 20 that's twice, and then 2 that are not. In C, all the values are just different, so that one has no mode at all. 7A, create a data set of at least 5 grades that has no mode. So I just went 50, 60, 70, 80, 90. I even did like an even spread of them just to do it. It actually made it easy. Maybe there's really no point in that. All right, B, create a data set of at least 10 quiz grades that has 2 modes. So I had 83 times, 93 times, but then the other 4 I only did once each. All right, 8. It's an odd question here because I don't know how you would use this like in advertisement. I think that's the direction that I was going for, but the question at the end, I'll get to that part first, is what is the mode of the 47,000 ticket prices? Okay, so if you're looking for the mode, then you're looking for the most common one. So you get 2,000 tickets at that price, you get 10,000 tickets at that price, and then you got 35,000 tickets at that price. So by mode, it's going to be a $20 ticket price. All right, and here we are getting to the best of all this stuff. So again, you might have remembered mean and median and even mode from like way back in school and how to do those, but what's the point of bringing up now while you're in a college class is because of how we look at the data and how we use those numbers to describe the data that we've got. Okay, in this table, what we have is a list of salaries at a dental office. We have all these values up here. Okay, so you've got cleaning staff, you got clerical staff, dental assistants, dental hygienists. So here's all your different pays that go along with them. And that's looking like a pretty good job right now, well, aside from coronavirus. But anyway, you got to do the calculations. I didn't write down all the work, but here's what you get. If you add all the numbers together and you divide by, does it tell us how many? You got to divide by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you add all those up and divide by 10, you get $42,200. The median, however, notice that we were really cool here and put the numbers in the order. So that way, so the median, remember there's 10. So that means I'm looking at 5 and 6 as the middle. 1, 2, 3, 4, 5, 6. These 2 are the middle, so that's why I wrote the A right here. These are going to be the middle numbers, so we're going to split the difference, which is going to put you at $38,000. And there's not that big of a difference between those 2, right? So whether you want to describe it as mean or median, yeah, that's what it is. I'm starting to think like, well, what if we looked at subgroups, but that wasn't the point of the activity. Okay, B, suppose that we add the 2 dentist salaries, right? The big dogs that are there that own the place, where they're going to make a lot more money. $150,000, $160,000, right? A lot of money that they're making. So if we add them to the list, we want to see how much the numbers change here. So now for the mean, you have to add all these up together. Then you're going to divide by 12 because you got those 2 numbers in there. And that's going to actually increase it from 42,200 to 61,000. Right, and I think that'll make sense because we added a couple numbers that are larger than the rest of them. And then when we divided, it's like, you know this with grades. You throw in 100 when you've had a lot of 80s, you throw in 100 and your grade's going to jump up when we average them. Okay, so we see that. But here's what's really interesting about it is the median. When we start looking at the median now, okay, so go back to the beginning with part A, that $16,000 employee canceled out with the 74,000, the lowest and the highest, and then they canceled in. Okay, so now the 16,000 person is going to cancel out that dentist at 160,000, and the 25,000 is going to take this one out. So at the very, very beginning with the median, those two big values just, in a sense, get eliminated. They're just eliminated really quickly. Okay, and now that's going to take us to, I was trying to block it off here, but it's going to be these two in the middle. You've got 1, 2, 3, 4, 5 above, 1, 2, 3, 4, 5 below. You still have 2 in the middle. So you'd split the difference, but they actually are both 40,000, so it's still going to turn out to be 40,000. So let's look at the comparison. When you add in these high values, also called outliers, when you add in the outliers, the mean is going to see a big pull in the direction of the outlier. I mean, we're looking at about 50% of that change all the way up to there. But in the medians, when you add outliers, you're not going to see too much of a change. There's always a chance that there's a big jump between some values when you shift over, but normally you don't see much of the median. So in your world, you're really used to doing averages for everything because we trained you like that in school. But the medians have the value of giving you a better number when you've got outliers. All right, C, which measure, mean or median, was not much change? That would have been the median. Which one was changed a lot? That would have been the mean. So I already answered all that. And we get to the final part here. This is it. Okay, graphs, symmetric, skewed out to the sides. Each of these have the medians listed in there. Remember, median is sort of like breaking up the space, the area that we have. So there's a histogram that would sit underneath this, but we're just looking at the curvature. The median is going to split the area in half, and I think that's easier to see in the symmetric. That's going to split it there. In the skewed left, it's not going to be at the high point because you got that tail that goes over this way. So it always ends up being moved a little bit in the direction of the tail, just a little bit, out that way, and then the opposite for the skewed right. Okay, remember that means are much more affected than the medians are, okay? In the symmetric graph, I might as well answer that one right now. In the symmetric graph, the mean is still there. It's balanced, right? So when you average everything, it's still going to fall in the same spot. It's still going to be there. But when you have data that's skewed, here's our example. Let's do this one with the dentist. You had a median value of the like 42,000-ish area, but when it got the dentist added in there, the median was at 40,000, and then your mean was actually further out over here. It got pulled in the direction of where those higher salaries are. So if you have something skewed left, you'd expect it to move the mean to the left of that halfway point there. See, median is based on the frequencies and the heights and all the area, but the mean is actually taking into account what those values are when they get averaged. All right, and then last is the mode. The mode is the most common one, and I told you earlier that it's kind of a neat one and how it shows up here. It is the peak. Right, that's the highest bar, which means that must be the most common thing that we get. So this one's all symmetric, they're all the same. And then your skewed, you're gonna have your mode. At the high point, your median is gonna move in the skewed direction just a little bit. And then your mean is gonna get pulled out a little bit more into the direction of the skewed. The actual spacing from the mode to the median to the mean, that's not the important part. They're not equally spaced. There's no rule that goes along with it. It's just that there's this one truth, though, that if you're skewed, your mode's at the peak, your median's next, then your mean, and those are both in the direction of your skewed direction.